Okay, good morning everybody on double microphones. Thank you for being here, all of you. I'm very grateful also to be invited to give this talk. Slightly nervous to give the first talk, knowing myself I'm going to be talking about something that I'm very enthusiastic about, but that is slightly geeky as well. So I've tried today, not knowing precisely what kind of audience we have today, to sort of do things in overview. So I'll be talking about what I would call advances in quantitative climate reconstruction using speleothem records. What that is will explain itself while I talk about it, I would say. Quite a few people here on the list of contributors, and these really are only the people that hands-on put stuff into this talk. There are actually many more who contributed in many ways. Okay. Let's dive straight into it. Yes. To start slowly, I thought, okay, let's show a cave, right? So these are kind of the caves that we kind of understand, right? A nice, warm and humid climate, and so green. This is in Brazil, Caverna do Diabo. And then you typically get these caves that have a lot of water in them, and there's a lot of growth of beautiful speleothems. And what are speleothems? I think most or everybody probably knows that here, but these are these things that grow in caves, stalagmites, stalactites, and so on. And we use them as Paleo-Climate records. So beautiful pictures like this is the kind of thing that we all understand. I believe there must be places in South Korea that look very much like this. Slightly less normal is a situation like this. Here we are in northern Saudi Arabia, and as you can see in the photographs, we've got camels, we've got sand, very typically northern Saudi Arabia, you would say. But then funny enough, on the top left slides, you can actually see that when you find caves there and you go underground, you bump into quite healthy looking speleothems. Stalactites on the left photograph and some beautiful stalagmites on the right photograph. Granted, they look a little dusty because they're not very young, because in the current climate of Saudi Arabia, there's no way that we can grow speleothems. So these things are old. This is also sort of my setup to the link to archaeology, because you see these three guys down there on the photograph. That's Mike Petraglia here today. Hi, Mike. And that's Hugh Grocott and Stewie, or Matthew Stewart. And if you find these three people on one single square meter, you know that there's an archaeological interest in this area. And this actually is the entire reason why this project started to begin with, and I was a passerby on it until we started hitting things like this, and it became really interesting. I have an example of this in my talk. Let's move Mike to another continent and to another reclined position, because Mike's carrying the heavy let's say, task of keeping everything working. This is Pangaea Saidi. This is eastern Kenya, coastal Kenya, and it's a fantastic archaeological site in a cave setting, where I ended up, you see me right here, trying to provide, let's say, stalagmite paleoclimate records to go together with this excellent archaeology. Okay, so these are the links which make me so happy to be here today, in between paleoclimate, archaeology, and things like that. Okay. Right, so speleothems, that's stuff that makes me really excited, and why is that? Speleothems as a paleoclimate record have gained a lot of traction over the past, well, decades, I might say. The field has been doing this since the 1970s, more or less, but there's been considerable extra interest in the past few decades. And there are two pillars under the success of stalagmites as paleoclimate archives. First of all, we can date them really, really well. And Rineke Wij, who's chairing today, is one of the absolute specialists in that field. She'll be talking about that a little bit more, I'm sure. What we all know pretty well is uranium-thorium dating, which is good for, say, let's say the past 500,000 years. And in principle, not a new technique, uranium-lead, but a difficult technique for speleothems is something that we're seeing more of lately, and I have an example of that. That will be this in my talk that I will show you. Okay, so really beautiful material for dating. Number two, of course, if you can only date it, there's not much. So you need some sort of proxy records. So we need something that we can measure on this that tells us about climate. And the simple fact that it's calcium carbonate to us is very useful because we have many, many, many proxy records for calcium carbonate that somehow we can link to paleoclimate. So there's a large base of literature already on speleothem paleoclimate records with fantastic high detailed records. But the thing until today has been that it has been kind of difficult to get really quantitative paleoclimate information out of these. So we get beautiful records of climate change, but if you want to know how much temperature precisely or how much hydrological change precisely, we always were in a difficult position to say that. And that's what my talk's going to be about today. To illustrate that thing, I always like to show this graph. This is an iconic, one of the earlier, longer paleoclimate records from Israel in this case. It shows a very commonly used technique, the oxygen isotopes of speleothems. Axel just showed one, and here's another one. And here you see we have 160,000 years on the x-axis. Here we go. And these are the oxygen isotopes. And if you know where the glacials and interglacials are on this scale, you immediately see that that thing on the longer time scales is sort of varying with glacial interglacial variation, which we find completely normal because we expect there to be a temperature effect on the oxygen isotope composition of calcite. What we also see in here is on a finer time scale, the S1, S3, S4, and so on that you see there, those are sapropel events in the Eastern Mediterranean. Those are hydrological events. Those are events that don't do too much in temperature, but they do a lot in the hydrology. And what we see happening here in the oxygen isotopes of this stalagmite is that also these sapropel events have a very strong effect on the oxygen isotope composition of the stalagmites. So here we have the typical mix, hydrological information, temperature information, and very difficult to pull them apart quantitatively. Okay, so we need to know either the latency of cave drip water or the temperature to be able to deconvolve this entire thing. And that's what we're going after then. To simplify matters, if only for myself, this is what I wanted to talk about today. If we look at speleothems, we have until now been looking mostly at calcium carbonate because 99.9% of the speleothem is calcium carbonate. So we get all these beautiful records, but it's not easy to get something quantitative. Although recent advances in clumped isotope analysis actually have been getting very close to proper paleotemperatures from speleothems as well. What I'll be talking about today is the water, which happens to be my personal hobby, and the organic carbon that you can also find in speleothems. The water in speleothems is available in fluid inclusions, microscopic cavities in the calcite that contain water. And if you can reach that water with whatever technique you use, you can actually study that water and try to get climate information out of it. We'll be doing that first. And then at the end of my talk, if you're still alive, we're going to move very quickly to the organic carbon that we have in there as well. And I'm going to be focusing on one technique in particular, TEX86. It's very well known for paleoceanographers, not so well known for people that work with stalagmites, but it works as well. I'm going to show some examples. So if you're okay with that, that's what we're going to be moving into. Fluid inclusion, isotope analysis. Okay, so speleothems contain fluid inclusions. There's an example in this photograph here. You can see they're very small, and you have to make a thin section, look with the microscope, and then you can actually see them. If you can get that water out, you have a record of drip water in the cave. And what we actually believe is that that drip water represents the isotope composition of the rainfall above the cave at the time that that water is dripping. So the idea is that we get a paleo rainfall isotope record here if we do everything right. Kind of like ice cores, but then in places where it's not cold. So that's kind of cool if you can do that, right? So the trick then is you have to get it out. No, let me first start here. let's say we get that done and we get these isotope compositions, right? So what does it tell us, right? So then we know the isotope composition of rainfall. Well, what we know about it, and I'm not sure to what extent this is known here, if you have hydrogen and oxygen isotopes of rainfall in the climate system right now, we usually expect them to fall on a particular line, which we call the global meteoric water line. That simply is how the Earth system works. No matter whether the rain falls in America, it falls here or wherever, we would find ourselves with the rainfall on the line like that. But depending on where you find yourself on the line, you can get some more information. If you're down here on that line, you probably have cold conditions, or you would have had a long atmospheric flow path over a continent to bring that rainfall to that cave. If you're up here, it's either warmer or short path. And if you're on a line like this, that we have right here, that's a so-called evaporation line, you may be looking at a system which has experienced evaporation after the rainfall events that you look at. So this is the kind of space in which we can start interpreting these data if we get them. Okay, and how we get them, that's brute force. This is a crusher, like a nutcracker almost, but then in a controlled environment. And there we put samples in, like discrete half-gram samples of pieces of speleothem that we then crush. We open the fluid inclusions, the fluid comes out, and we then analyze that quite simply in a Picaro analyzer, which brings us the hydrogen and oxygen isotope composition. I make it sound a little easier than it is, but currently there are quite a few labs who are able to do this and get good data. Okay. From there straight into an example, which is one of my favorite examples, because that's the stuff that we've been doing in Saudi Arabia. So we're going to go back to Saudi Arabia here. In the very colorful picture, just a reminder of the archaeological importance, or maybe the evolutionary importance of Saudi Arabia, because that large zone that we have here effectively separates Africa from, let's say, Asia, for example, when it's dry, and when you are able to make that wet, so green Arabia and green Sahara periods of time, you can actually generate some movement in your systems. And this is why, for example, archaeologists are very interested in this. We have a record from Saudi Arabia. It's right there. And when we started dating that, we had no clue, and it took us a long time, because eventually we found out that we had more than 7 million years of recurrent wet phases in that particular area, so in the middle of Saudi Arabia. Where am I in time? So far, so good. Okay, that's okay. I'll just speed on. This is, after a few years of time, a very long and tedious dating thing, because we needed uranium lead, which is not a difficult thing to do, but it went quite well. 8 million years of time on the x-axis, as we have it here. We have these oxygen isotopes of the calcite of the speleothems on the y-axis, and then here you see that we have quite a number of these intervals in which the Saudi Arabian desert actually was relatively wet, because to grow speleothems, you need a minimum amount of rainfall to get it done. You need a soil, you need vegetation, okay, the kind of conditions that you need to sustain life. So here we go, and we have for a long time in this history, the Miocene and the Pliocene, we have what we would consider to be very low oxygen isotope ratios. Okay, and then towards the end of this record, we see that we also have these oxygen isotopes. We still have the low ones, but we get much higher ones as well. And we kind of believe that this typically is related to how we normally would interpret the oxygen isotopes of calcite. 20 minutes, thank you so much. I'm in good waters. And so basically what we believe is what we're seeing is that we see this aridification trend that everybody is talking about. We all agree on that thing is there, right, on timescales like this. The point again is, if I want to interpret this, so how much of this is temperature, how much of this is hydrology? We suspect it's hydrology, but we don't know. We have to figure out with different means, and that's what we use these fluid inclusions for, because that's what we did next on this data set. And then the fluid inclusions, remember I was talking about this global meteoric water line, that's that thing. If it's rainfall, it should be on there. And here are the data that we have in that project, and all of the filled symbols that you see there are fluid inclusions from the stalagmites as we have them. The color coding is by age, so 7 million years in blue, and then it goes towards red when you go to younger. And there also are a bunch of symbols up there, which are the open symbols, and that is modern rainfall. There are a few things that you see here very clearly, that the paleo rainfall was isotopically completely different from the modern rainfall. The second thing that you see, if you look in a bit more detail, is that the older speleothems are probably furthest down on the line. Yeah, and then towards that direction is what you go when you go to younger, and this would fit this whole idea about the aridification trend also in the isotope composition of rainfall. Because how do you interpret this? It is virtually impossible to get rainfall isotope values like that if you're not in some sort of a monsoonal system. So we actually believe that in the early history of this site, there was a lot of rainfall that came directly from the ITCZ, so it came directly from the monsoon, if you would like. And in modern times, this area is outside of the reach of the monsoon, right? And that through time, we probably lost the influence of the monsoon gradually into this system, leading to this enormous shift in isotope compositions that we see here. Is this cool? Well, to me it is, because this is the first time that we can actually pin the isotope composition changes that we see there on something that we can really say, this is the hydrology. It's the rainwater that does it, and it's not so much the temperature that does it. Okay, so this is the relevance of that thing. If you then plot it, as you would normally do, with some global records, then you kind of confirm that what seems to be going on in terms of drying in our area is sort of in line with the kind of drying in the Sahara. We believe the Sahara and Saudi Arabia sort of go together in this drying trend, so that all fits. There's this interesting gap around here, which I like a lot, because that's where we have the so-called Messinian salinity crisis, which is when the Mediterranean basin dried up, for example. And of course, the entire system also is in line with the amount of ice on Greenland, let's call it that way, right? So the cooling of the northern high latitudes are probably the mechanism that drove southward this ITCZ influence on Saudi Arabia through time. So this is the interpretation as we have it now. Okay. So now I was only talking about hydrology, and we should also talk a little bit with these fluid inclusions about temperatures. Daniel, you're talking later, right? You'll be talking about some temperatures, but not these temperatures. You'll be talking about the TEX 86, right? Okay, so let's talk about fluid inclusion microthermometry temperatures first. This is not my specialization, but it's super interesting stuff, so I need to show it to you. And it has a relevance to Saudi Arabia as well. First of all, microthermometry, for geeky geologists, this is something that you do with a microscope. You look at fluid inclusions. You have a special microscope with which you can change the temperature of your sample that you're looking at. So here you see fluid inclusion, and this is a typical cycle that you go through when you do microthermometry. First of all, you take your sample and you look at it under room temperature. That's your sample at the left. And then you say, that's nice, it's completely filled with liquid. And then you bring the temperature down. You bring it down to a temperature that is under the temperature that you expect it grew at in the cave. Okay? And when you do that, you bring it to a so-called metastable liquid phase. Nothing happens at that point, but if you then shoot at it with a very fancy femtosecond laser, you give it a little energy kick, you provoke the formation of a bubble. That's right there, a vapor bubble, because it is so cold. And once that bubble is there, you then look at it under a microscope and you start cranking up the temperature again. And when you do that, you go up in temperature at 15 degrees Celsius, it's still there. Here, for example, at 17.4, it's gone. And that so-called homogenization temperature is very close. There's a tiny correction necessary to the temperature at which the speleothem grew. To me, this always sounds a little bit science fiction-like, but it's a fantastic method, actually. It works really, really well, but not in every sample. Okay? So when we have this in place, and these are our fundamental assumptions, so it's the density that we are looking at, and the density is fully determined by the temperature, and the fluid inclusions must have remained closed systems through the lifetime of the speleothem when you have it in your lab. Okay. Now, when you do that, you do that multiple times for fluid inclusions. You can look at a single fluid inclusion and do that, for example, 40 times in a single layer. you get distributions like this, and that gives you temperatures, and the scatter is significant, but if you look at enough of them, you can do your statistics and you can get down to pretty precise sort of analytical precisions, okay? Which is, in fact, this is the most precise that I know. Just an example of a story by Fernandez et al. 2023, who did this game, and they really the thing to look at right now is the data here in orange, because that's the microthermometry data over, let's say, LGM to modern, if you like it. And these are typically the data that come out of that, the temperature data. Incredibly tight curve, and you compare that to the Antarctic temperature anomaly work, and that's nuts. This is an example from Borneo, and this shows how fantastic this stuff can work. The drawback, it's incredibly time consuming. You can do one temperature per 2 days, something like that, yeah, but a very good one. Okay, to bring it back to Saudi Arabia, because this is what we're working on right now, and being enthusiastic about it, I wanted to show this to you. This is just to show you that when we use this technique, we can actually go back to more than 7 million year old speleothems, and this still works. It's quite amazing. And why do I believe this still works? Well, the microthermometry data, so again, 8 million years as we have it here. So a selection of samples from that record that I showed you before. In red, the microthermometry data, compared to in blue, this super new fancy clumped isotope, dual clumped isotope system that we believe is providing good temperatures as well. And in the layers where we have them both, we have pretty excellent comparison between the two methods. So we actually believe that here we can play this game. We can look back more than 7-8 million years in Saudi Arabia and provide you with temperatures on the continent. Okay, enough of a sales pitch for that, I would say. If you're still alive, we're going into the third and last bit of it. We're going to move to the organics, because that's exciting, and actually this is where I should have called you out, Daniel, because that's the stuff you're going to be talking about as well, right? Okay. TAX86 speleothermometry. Actually, it's an established and not so difficult method to do if you know your organic geochemistry, okay? It's been used a lot in paleoceanography, and it's been used not so much in let's say, continental paleoclimate science. Well, in lakes, but not in speleothems. And I'm going to show you a little bit what we're doing right now and what kind of records we got with that. So another way into quantitative paleotemperature data from speleothems. Okay, so what is it? I'm not an organic geochemist. Let me start there, right? This stuff is based on GDGTs, and I'm not going to pronounce what it really is, but you can read it there. Yeah? And GDGTs are organic compounds that are typically produced by archaea, a type of bacteria, one might say. These archaea are virtually everywhere. And if you find these compounds, then you know that these bacteria were there. We find them in speleothems. So you can take bits and pieces of speleothem, dissolve them, get the organics out, and find these GDGTs. And it's been shown already that in principle, the typical distribution of these GDGTs in a ratio that we call TAX86, I'm not going to show you the details on that today, is a very good indicator for temperature. To get it right, you need a calibration. So you have to do a lot of work with caves of which you know the temperature to get a good calibration, but if you have that, you actually have a very good paleothermometer. Our working hypothesis is that these archaea that produce the stuff that we're looking at were actually living in the cave and were probably sitting on the speleothem. They like it wet, so they might have sat under the dripping water, precisely the right place where we want them to get the temperatures that we are looking for. Okay. This is the kind of calibration that you can make. So here, this is just an example of in gray the published data by Baker et al. 2019. And in red, the new data that we added to it over the past few years. The point of this slide is that they're indistinguishable, which is nice. Different labs, different ways of measuring same calibration. The analytical precision is really, really good, better than 0.5 degrees Celsius typically, but because we have a calibration that we need to deal with, that's where most of our uncertainty is. So typically, between 1 and 2 degrees Celsius uncertainty is what we're dealing with when we do analysis like this. What's kind of cool about it is you can do many more in a week. So if you get angry in about a week's time, you can do between 20 and 40. and get a very large amount of data if you want to have that. Okay. Some examples, I guess, because that's always most fun. And Jasper, you're here. I cannot go around these data because this, I believe, was the first longer time series data with TAX86 that was ever published after Andy Baker's 2019 paper, done in the labs in Mainz. And what Jasper's been doing, he was looking at a Chinese record at pretty high resolution, MAS6 to MAS5, so really deep glacial to warm interglacial conditions. And we were interested in hydrological and paleo temperature change in that system. So what Jasper did, he reconstructed, in fact, the response of the monsoon system to the penultimate deglaciation. This is how you could see it. And he linked that to a significant atmospheric circulation change because we had these new data, we could play that game. Okay, so very colorful. So what does it look like if you go in detail? Let me draw your attention to the right side of the graph first. Jasper, I always have difficulties explaining the details of this, but the good thing is you're here. But what's really cool about this record, you see the wiggly line. Those are again the oxygen isotope data of, I'm in your way here, right? The oxygen isotope data of the speleothem calcite, so that's our reference if you like. And then there are two types of data in here. At the very top, we have the TAX86 temperatures as they were analyzed. And those are the dots that we see there in two different colors because we have two different stalagmites that together make this record. And then below, it's the same samples essentially, because that's what I didn't explain yet. We can do two types of analysis on the same sample. These are the fluid inclusion isotope ratios that we did on the same record. So this is the hydrology and this is the temperature, if you like. Now, what Jasper was able to see is that, first of all, we were able to detail the temperature changes that we find through this glacial interglacial change and quite precise, in fact. And Jasper was also, you had the first paper that had the dual clumped isotope temperatures in. And maybe I should point out the uncertainties we typically have on the TAX86, which are pretty small, as compared to the uncertainties of the dual clumped isotopes. Dual clumped isotopes are great, but they have a slightly higher uncertainty on them. So it's always nice to be able to make these comparisons. And here we actually see that everything is within error of each other, and particularly the TAX86 data really details very nicely what the actual change of the temperatures is at that point in time. What Jasper also showed was that the response of the hydrology was slightly different, and this actually was the bit where he was able to detail how the Indian summer monsoon was disconnected from our system just in Heinrich 11. This was basically the thing that we could do. It's a bit detailed, it's a bit geeky perhaps, yeah, but these are the kind of things we're able to do right now because we have these data quantitative right now. And before we only had the oxygen isotope data and we did not really know what was what, okay? Just the latest, I had to show this because this came out like last week. Jasper, you haven't seen this one yet, I think. This is an example and it's a simpler plot, so I just wanted to show it to you. This we have time. This is the deglaciation. Actually, Axel showed a little bit on that as well. And here we have a typical Younger Dryas. We have a Bulling-Allerode, and we have the Holocene coming in, if you like. Everything visible again in the oxygen isotopes of the calcite. And this is the kind of record. If you have a fast-growing record, this is the kind of resolution you can get, and we're currently improving the resolution even further of these temperatures. Oops, sorry about that. I'm messing it up right now. Up of these TAX86 temperatures that you can get. I mean, this is a very surprising plot to me because we're in Brazil right here, and I see a rather large temperature effect in the Younger Dryas, which I hadn't expected. But this is something that we're looking into. And again, this is something we can look into right now because we have these data. I think I've bugged you enough. I'll leave you with the summary. Actually, no, there's something I need to say about the summary. So we've made quite significant progress over the past decades in quantifying these typical climate indicators that we can get from the speleothems. And I find that rather exciting personally because it really is a point that we had to go through to be able to get better reconstructions and perhaps also get better connections to what the modeling world is doing, because there's exciting things going on there as well with isotope-enabled models and things like that. And if the proxy people cannot provide the data that have the detail to compare the models with, then we cannot compare anything at all. So this is what I kind of like. And I'm very excited to talk to people about this modeling sort of approach to how we do this. And having said that, I think you can read the rest for yourself. Thank you very much for your attention.